Hi folks, today we're going to talk about domain and range and symmetry. So domain and range should feel pretty good. You should feel pretty good about that, especially after we did the transformation section. And then symmetry, we're talking about odd and even symmetry, which I'll explain again in case you don't remember it from our pre-calc days. So we're talking about the symmetry, domain and range and symmetry of a function. So just a reminder of what a function is. So a function is, he describes it as a machine, which is how I've always described it too, where you have these inputs that go into the function machine, an equation, and you get an output. All right. So when we're looking at these independent variables that get busted into the machine and then get calculated and come out as what we call a dependent variable. The question of today is, what sort of numbers are legal to put into our function machine? If it's x squared, any value is legal. We can put anything into an x squared. We can put 7, 9, -2, 0, 3/4. Anything can get squared. But there are certain functions that you can't put any number that you want into. I mean, I think square root is one that I think of off the top of my head. So let's talk a little bit about the domains that we run into, some of the problems we have with the domains. So the first one, this should go back to our pre-calc days. Dividing by 0 is bad. There's only a certain number of... You cannot divide by 0. I'll just leave it at that. I don't want to over-explain it. You can't divide by 0. We also cannot take even roots of negative numbers. Notice it doesn't say just square root. It says even root. So fifth roots don't have the plus or minus problem. Fifth roots don't have a problem in their domain. But sixth roots do. 7 roots don't. 8 roots do, and so on and so on and so on. And then finally, the one that we probably used the least last year is you cannot log a non-positive number. So you can only log positive. So 0, you cannot log 0. And then this one I think is kind of a cheap shot, but it's definitely worth talking about. Explicitly undefined values in piecewise functions. Excuse me, I'll talk more about that with an example, but you remember piecewise functions, that's where you have like 3 equations, and then at the end it says x is less than blah, blah, blah. I mean, there's certain points in there that if they're not defined by the function, then they're not part of our input. They're not part of our domain. Just a quick review of symmetry. We talked about this last year. We talked about it when it came to oddness and evenness, and our main focus was the type of symmetry that the graph had. So there are 2 types of symmetry that we're going to talk about in the world of functions. The first one is called y-axis symmetry. This is for even functions. The other type of symmetry is called origin symmetry. These are what we do for odd functions. So when we're looking at a visual representation of a function, in other words, if we're looking at the graph, graphs that lay on top of themselves exactly as they're folded along the y-axis are even functions. So I'm going to highlight that in the same color. So everything in green will be about even functions. Graphs that lay on top of themselves exactly if they're folded along the y-axis have y-axis symmetry and are called even functions. This is an example of an even function, because if I take this side of the graph and I fold it across the y-axis, I get the exact same picture. So if I were to highlight this, last year we called this reflective symmetry about the y-axis. This is what we call even function symmetry, or y-axis symmetry. Next up, graphs that look exactly the same when spun 180 degrees, or pi over 2 radians, around the origin have origin symmetry and are odd functions. So here's my graph. And when I rotate it 180 degrees, this side, I mean, really, I should probably, I don't know if I like this anymore, but I'm doing it. So it doesn't just mean one side has to rotate to the other. I should really show this going both directions. that the y flips back to the green, the yellow flips back to the green, and the green flips to the yellow, and makes the exact same picture. So this would rotate down here, just like this would rotate up here, and you'd get the exact same picture. This is what we call rotational symmetry about the origin. Origin symmetry or rotational symmetry is an odd function. And then we have lots and lots of graphs that don't have any symmetry. So this is just some peculiar function. This doesn't have, it's not even or odd. So there's the first way to test for oddness and evenness. What type of symmetry does the graph have? And this gets a little bit sticky later on. We're going to look at an example where if you graphed it on your calculator, you would think, here's an example. If you graph this on your calculator and you didn't have a good enough window, you would think this would have reflective symmetry, but it doesn't. So we're going to talk a little bit more about how to test and check to see whether or not they really do have this symmetry. And the way you think about it is you think about it in terms of the x values. So look at this x value and then its opposite x value. So this is x, this is negative x. What's our y values for these two functions? They have the exact same y value. So f of x equals f of negative x. They equal each other. So when I plug in x, when I plug in negative x, I get the same value. That's a way to test a function to see if it's even. So here's an even function. We've got something simple, x squared. What I can do, and I don't know, this is him just showing. These do not count as proofs. I'm going to actually cross them out. Those are not actual proofs. This is the proof that you would use at the end. So you would take f of x, you'd plug in negative x, and you'd clean it up. F of negative x is equal to negative x squared. Negative x times negative x is positive x squared, which is equal to the original function. These two are equal to each other. If f of negative x is equal to f of x, then you have an even function. Even because f of negative x is equal to f of x. When you plug in a negative, you get back the original equation. That's how we check algebraically for even functions. If we look at the next one, now we're talking about for odd functions. What was odd? It was pink. Now we're talking about odd functions. So let's just check it or talk again. How can we prove that odd functions are odd? Look what happens to x and look what happens to negative x. So here's my x value. Look how it's just below that tick mark. Look at my negative x value. It's just below the negative of that tick mark. So f of x, my bad, dang it, I'm going to rewrite this one. This should be f of negative x equals f of x. So you always plug in a negative x. And then what you get out tells you if you have an odd or an even. So f of negative x, when I plug in f of negative x, is exactly the opposite of f of x, is the opposite of f of x. Say this is 0.75, this is negative 0.75. Now what do you get when you're talking about a neither? That would be, I still plug in negative x, but that doesn't equal f of x, nor does it equal negative f of x. It's neither one of those are true. So going back to our notes, here's our function. He used f of negative 2. We should really use f of negative x. I'm going to plug that in. So I would say our equation is x cubed. So f of negative x would equal negative x cubed, which equals negative times a negative times a negative is a negative, which is equal to the opposite of my original function. My function is f of x equals x cubed. When I plugged in negative x, I got the opposite of x cubed. Therefore, I now have a odd function. This is odd. This is odd because f of negative x equals negative f of x. If you'll notice in his little notes here, he forgot a negative here. This should say f of negative x. There should be a negative right there. It should be negative f of x. Okay, so can a function be odd and even? No. Well, there is one function. It's kind of a boring function. You can try to think of that function on your own. There is only one function that is both odd and even. And it's the only function to possess x-axis symmetry. It's kind of a boring function. Think about it. Maybe you could figure it out on your own. But every other function is either odd, even, or neither. All right, so we got a little bit of work here. Now, he's done all the work for us. We're mostly just going to talk through it, and then you have to be able to do that work on your own later. So what are we trying to do? We're trying to find the domain, which means what? Look for problems. What are our problems? Let's go back to here. This is what I call the problems. X's on the bottom are a problem. X's under an even root are a problem. X's inside of logs are problems. So as we look at this function, do we have, let's highlight the second part and then find and justify any symmetry. So do we have any problems? Yes, we have a problem. What's our problem? We have an X on the bottom. This is a problem. So what would we do? This stuff on the bottom, then in the denominator, what can't it be? 3x cubed minus 12x cannot be 0. Which now this is something that we can factor and solve. So he did the work for us, so I'm not going to redo it. He factored out the common term of 3x. That left us with x squared minus 4. X squared minus 4 is dopes. So he factored that into x plus 2, x minus 2. Then he ZPP'd each one of those. And then he figured out that x cannot be 0, 2, or negative 2. So the domain is blah, blah, blah. This is not how I would write the domain. I would write the domain, and I'd like it if you wrote the domain the same way, using interval notation. So we can use every number except for 0, 2, and negative 2. So I can go from negative infinity up to negative 2, can't use it. I can go from negative 2 to 0, can't use it. And then I can go from 0 to 2, can't use it. And then I can go from 2 to infinity. You see why he wrote it his way, much, much shorter. But my way, I think, makes more sense in terms of what we're talking about. So it's up to you. I guess I don't really care if you want to try to learn that notation on your own. This is read x such that x cannot be 0 or plus or minus 2, and it's assumed that it's from all real numbers. But I'm going to write my stuff in interval notation, even if it takes a little bit longer. So remember, interval notation, who's missing? I can't use negative 2 on either end of this. I can't use 0 on either end of this, and I can't use 2 on either end of that, but I can use any other number. Now it's time to test for the symmetry. And the test for the symmetry is the same every single time. You need to plug in x for, you need to plug in negative x for x. So Corpy took our equation and he replaced all the x's with negative x's. Negative x, negative x, negative x. Then he cleaned it up. So a negative x on the top. What's a negative cubed? Still negative. What's a negative times a negative is a positive. Now, he did some factoring out and all this stuff. I would just look at this and say, all right, what happened to all of my signs? If I divide everything by a negative, that's what I would do next. I just divide everything. So what's a negative divided by a negative is a positive. A negative 3 divided by a negative is a positive. A positive divided by a negative. So we get this. How does that compare to our original function? These two equations are exactly the same. So f of negative x is equal to f of x, which means we have an even function. So let's talk a little bit about some of these phrases, some of these things we haven't talked about since last year. That's what this big box is full of. Most of the values that make the denominator equal to 0 are called discontinuities. We might remember that. What do we call most of our discontinuities? They fall into two categories. Hopefully you thought of holes and VAs. So the first one is the easy one to get rid of. These are called not easy to get rid of, sorry. These are non-removable discontinuities. These are our VAs. It's really hard to fix a VA in a graph. It's hard to fix infinitely many points that don't touch each other. This asymptote, I'd have to move all infinitely many of these points back up to these infinitely many and somehow tie them back together. They're very hard to fix. That's why they're called non-removable. Then we also have ones that are called removable. Removable, they said point discontinuities. I just think of it as removable discontinuities. These are our holes. It's really easy to fix a hole. You could just put a point in there and now you don't have a hole anymore. A couple of things to remember about what it looks like. This is kind of from our HASAVA. Remember when we made that little chart on the side of our paper with rational functions? That's where this comes from. If you plug in a if you plug in a number and you get a 0 on the top and a 0 on the bottom, this is what we call an indeterminate form. You're going to hear that phrase a lot. 0 over 0 is an indeterminate form. This is going to cause you to have a hole. 0 over 0 ends up making holes or removed. That one point gets removed from the equation. Let's say that you put in a number into your equation and you get something that's not 0 on the top, but is 0 on the bottom. That causes us to create a vertical asymptote, which are non-removable. So if I were to kind of organize this and bring it down to the bottom, let's take this whole section here about the discontinuities. I want to go from here to here. I want to bring it down here. We have three scenarios. We have when you plug in a number, you don't get a 0 on the top, but you do get a 0 on the bottom. This is a VA. Oops. When you plug in and you don't get a 0 on the top, but you do get a 0 on the bottom, that's a VA. When you plug in and you get a 0 on the top and you get a 0 on the bottom, this creates a hole in our graph. And then the third scenario is where we plug in and we get a 0 on the top, but we get not a 0 on the bottom. That creates this thing called a 0. And then, we also called zeros, we call these our x-intercepts. We call these our solutions. We call these our roots. All those are phrases that are the same thing. So I could tell right away when I plugged in 0 into this equation, I got 0 over 0, which meant that there is a hole somewhere. I don't want to go I could find it. It's at 0, right? Because he did already factor it for us. An x on the top and x on the bottom cancels. So there's a hole. But there's also VAs when you plug in 2 or when you plug in negative 2. All right, here's our function. Find the domain. Find and justify any symmetry. So again, I'm going to give you a chance to pause here and see if how do you find domain? You look, 3 words, look for problems, and see if this has any problems. Well, hopefully you notice this has 2 problems. First of all, we have a problem here. This is a problem. We have something, an x underneath the square root. So I would take whatever this stuff is underneath the square root, x minus 1, and it must be greater than or equal to 0. It cannot be negative. So then when I solve this, that means that my domain has to be greater than or equal to 1. I also have a problem here because we have an x on the bottom. Whenever you have an x on the bottom, that stuff on the bottom cannot be equal to 0. So x cannot be equal to 0. So I would take these two problems together and I would make up my overall domain. All right, so if you're greater than, look at, by the way, he did the same thing. There's the greater than or equal to 1. There's the not equal to 0. But think about it. If you're greater than or equal to 1, are you ever going to be 0? So these they work well together. So I would write the domain like this. X is, I'm greater than or equal to, so that's inclusive. 1 to infinity. That's the bracket. Here we go again. We're going to test for symmetry. How do you test for symmetry? Plug in negative x for x. So I take my equation. Everywhere there's an x, I'm going to replace it with a negative x. We replace this with negative x. We start to clean it up. Negative x is just going to still be negative x, and negative x times 3 is negative 3x. He then noticed that there was if you look at this and you compare it back to the original equation, you might say, oh, wait, everything switched sign. No, not everything did, right? This is negative 3x, this is negative x, and then a negative 1. Well, the x switched signs, but the 1 didn't. The 3x switched signs, negative 3x did switch signs. So you have some stuff switching signs and some stuff not switching signs. Therefore, f of negative x is not negative x, negative f of x, and f of negative x is not equal to f of x. So this would be a neither. This is neither even nor odd, because some stuff switched and some stuff didn't. A couple of things to point out here. I don't know if that's worth talking about. Function divided by 0. We can't do that. We got some imaginaries. We don't want to deal with any of that. Here's something worthwhile, though. Remember, our calculators lie a little bit. We have to be careful. Calculators lie, or at least they appear to lie. And graphs can sometimes be misleading. That's definitely true. Notice that this graph over here doesn't show the y values at or just to the right of x equals 1. So here's his calculator. He took a screenshot of his calculator, and on his calculator it just magically stopped there. But when he plugged in x equals 1, he got an answer. He got x equals 1 is equal to 0, even though our graph didn't go there. That's because our graph is too steep. And your calculator, I don't know whatever that means, it never wants to draw things with vertical lines. So this graph here, this part right here gets so steep that your calculator says, I can't even draw it because I'm not allowed to draw vertical lines. So it just stops it at its last not vertical spot. That doesn't mean that the graph doesn't continue. And then you might say, well, how do I know that it goes down there? That's why we do the domain. Our domain is inclusive until 1. So we definitely know it reaches down here until 1, and then it does stop, because 1 forward is all that my domain lives for. If you plugged in negative 1 into the negative 1/2, if you plugged in 1/2 into this, you would not get a result, because 1/2 does not fit within our domain. Here we go again. Domain. Find the domain and justify any symmetry. So I'm going to have you pause. I want you to try to find the domain on your own. At least just do the setup. Okay, hopefully you notice that there were 2 problems. We have 2 bad things going on here. I have this piece. This is a problem because it's a variable in the denominator. So pi times t cannot be equal to 0. Divide both sides by pi. We figure out that t cannot be equal to 0. Okay, so we right now have a restriction on our domain that t cannot be 0. We also have a problem here. We have a double problem. This is a double problem, not because it's the second problem, but I call this a double problem because we have a t on the bottom that's also underneath a square root. So I have to solve them separately. Or let's think about them separately first and then try to merge them together. So 4 minus t squared has to be greater than or equal to 0, and 4 minus t squared cannot be equal to 0. So if I took those two ideas and put them together, this is saying that you have to be greater than or equal to 0. This is saying you can't be 0. So what I could do is just restrict that to say that you have to be greater than 0. Because the not equal to 0 kills off this equal to 0 right there, and it just leaves me with the greater than. So now this is something that I can solve. I'm going to bump over the t, so I would get 4 is greater than t squared. Now I'm going to square root, and you guys might not be used to this move here. We're going to square root. Square root is on file. We don't need a water. We just need a plus or minus, which means 2 is greater than t, or negative 2 is less than t. Why did that switch around there? Because of the negative. Remember, anytime you deal with a negative when it comes to an inequality, those are going to switch around. Now, I could put these together. I should really say and, not or. So negative 2 is less than t, but what is t? T is less than 2. So now we can put all that together in one statement, and we can use that statement to now define our domain. Our domain is negative 2 not inclusive until 2 not inclusive. Pretty tough. That one's pretty tough, but it's not beyond your skills. It's pushing the limits, but it's definitely not beyond what you can do. All right, test for symmetry. It's the same thing every time. What do? Plug in negative x for x. So let's see what Corpy did here. He replaced, it should have written t there, but we'll have to live with it. Plugged in t for all those, so that's going to stay negative. There's going to be a negative. A negative divided by a negative is a positive, so that's where that one went. What happened to this negative? Well, negative squared is a positive. So yeah, this is the same as the original function. So my original function and the function when I plugged in negative t is the same as the function when I plugged in t. So we've got an even function here. And you can go back and read some of this stuff if you're having a hard time understanding why this works. All this works right here. That's what Corpy explains in those pieces.